All right, vectors. Here we go. Okay, vectors. Um, there's actually quite a bit that changes in vectors from physics 1 to physics C. Okay, and for that reason, I'm going to kind of go through it. Okay. Um, so rectangular and polar notation, you're not doing a ton with polar notation, but you do need to recognize it as polar notation. All three of these right here are rectangular notation. Okay, are different forms of representing vectors as rectangular. There's actually, I think, three. When I was in college, I learned of three different coordinate systems, and there was rectangular, which I think we called Cartesian, polar, and then there was also cylindrical, which is a completely different one. But you only need to know rectangular and polar you don't even really need to know very hard. You should know that. So like if you were to represent a vector as an ordered pair, you'd use this funky like really cool bracket here. So I'm going to use it for like this vector A right here. The ordered pair in general is going to be the x component and then the y component of the vector, okay? Or a sub x, a sub y. I probably should have written it like that, okay? Um, so the x component of this vector is 1, 2, 3, 4. Okay, so 4, comma, 1, 2, 3. So it goes up 3. Okay, so the x component and the y component of the vector. Okay, a column vector is going to look kind of like a matrix. Okay, and it has the x component on the top and then the y component on the bottom. Okay, so the x component is, we already found it was 4 and then 3 on the bottom. Boom, there you go. That's a column vector. Pretty straightforward. Okay, nothing too crazy. The unit vector is brand new. Okay, unit vector is brand new. You haven't seen this before, more than likely. Okay, but what you would do is if you've ever seen the like I's with like pointy hats or the J's with pointy hats, that's what unit vector is. Okay, um, the unit vector is a sub x I hat plus a sub y j hat. Okay, and that's literally what we call them, I hat, j hat, okay? You take the x component, multiply it by I hat, you take the y component, multiply it by j hat. And I'll explain more about unit vector here in a little bit, okay? But you would do a sub x I hat. Okay, so that's going to be 4 I hat plus 3 j hat, okay? And then polar, the way that you represent polar is the magnitude of the vector at the angle of the vector. So in this case, the magnitude of the vector, um, it's a Pythagorean triple, so the magnitude is 5. Okay, 5 at what angle is it at? It's about 37 degrees. Okay, and that's polar notation. Okay, okay, that's polar notation for you. Okay, let's look at how to find certain aspects of vectors, right? Using we can do components, magnitude, and direction, right? Well, if the angle of the vector is measured relative to the x-axis, hopefully from physics 1, you remember that the x component of the vector is the magnitude of the vector times the cosine of that angle between the x-axis and and a. I hope you remember that y is the same thing but sine instead. Okay? Sine theta times a. Or theta of a, sorry. Magnitude is Pythagorean theorem, right? If you have the components, the x and the y components, they make a right triangle, so you Pythagorean theorem it. A sub x squared plus a sub y squared. And then you take the root of the whole thing, because if you don't take the root, it gives you the magnitude squared. You don't want the magnitude squared, you want the magnitude. Okay? Theta, to find theta, remember to find theta, we would do the inverse tangent or the arctangent, okay, of the y component a sub y over a sub x. Okay? There's a really important note to make, especially for theta right here, okay? If a sub x is less than 0, so negative, okay, you have to add or subtract, okay, 180 degrees from what the inverse tangent gives you. Okay? You have to add or subtract 180 degrees from what the inverse tangent gives you. So it doesn't matter which one you do, right? It doesn't matter if you do, you know, it doesn't matter if you do, if you add it or subtract it. Okay, it doesn't matter if you add or subtract it, because what that means is that so if you add 180 or you subtract 180, you're really just flipping the direction of it. Either you're going to get like a negative angle or you're going to get one that's over 180, which is fine. It really depends on the system that you're using. So for like example, for A here, I'm given it goes from 0 to 360, right? It goes from 0 all the way around to 360. So you could do either one, you'd be fine. You would just have to do like, so for example, if I had to subtract 180, then I would get a negative angle, and I know I just have to count the angle going this way. So in this case, it'd actually be easier to add the 180 because it actually goes all the way around. But if it only goes up to 180, I would say maybe subtracting or adding or subtracting it would probably be better. Okay. Okay, let's practice a couple of vector operations. Okay. First off, okay, we're given a is equal to negative 3 I hat minus 4 j hat. B is equal to 4 I hat minus 3 j hat plus 12. Oh, what does the k hat mean? This means the z-axis. Okay, it means that there's a component that goes in the z-axis. We pretty much never really use the z-axis in physics except for in these vectors parts, okay? And then we have a polar notation. So let's figure out the magnitude of A, okay? Magnitude of A is just going to be root, 3 squared plus 4 squared, okay? It would technically be negative, but the squares are going to cancel out the negative, so it doesn't really matter. And that ends up giving us 5. You don't even really need to do math for that if you know that's the Pythagorean triple, okay? B, okay, B, I'm going to have to, so you're just going to add all the components. So it'd be 4 squared plus 3 squared plus 12 squared, all under the root. Okay, you don't just stop at the first two. You have to do all of them, and you should end up getting 13. Okay, as the magnitude of that vector. 2 times a, you can actually just multiply. I mean, we forgot what a is, right? Then it's 5. But if you do it with components, right, you would have to multiply the components by 2. So you would end up doing the root of, it should be 6 squared plus 8 squared, and this actually also gives you 10. Okay, that gives you 10. And that's also Pythagorean triple rule, right? Multiples of it give you multiples, okay? To get the theta sub a, we would need to do the inverse tangent of the y component, which is negative 4, over the x component, which is negative 3, and that gives me 53 degrees. Now here's the thing, that's not my answer because that is going to be in quadrant 1, and we can tell that because both of our coordinates are negative, it should be in quadrant 3, right? So what I need to do is I actually need to add or subtract, okay? Add or sub, okay, 180 degrees, okay? And when I do that, I can get either theta A is equal to, I got negative 127. Okay, if you add 180, you're going to get a different number. Okay, but I subtracted the 180 from that to get negative 127. Okay, okay, so there's that. Okay, if you add it, you'll get a number that's over 200. I don't know exactly. I just did it this way. Okay, I don't remember off the top of my head. Okay, this right here, this weird thing right here this means angle of. Okay, angle of. Now here's the thing. If it's 2a, right, you could do the tangent all over again, and that's fine, except you don't even need to. Because if you're making the vector longer, right, 2a is just making the vector longer. As we saw here, we're just making it longer. But the components are the same, which means that the angle is not going to change. So angle doesn't change, okay? So 2a is same direction, okay, but longer than a, okay? So it'd still be negative 127 degrees, okay? What about for negative a? Well, negative a is just flipped, right? So it's opposite direction as a. So you would have to add or subtract 180. Hey, wait a minute. Add or subtract 180. I did that already. It's 50. It was 53 originally, right? Okay, x component of c. Okay, x component of vector c. Well, we're given the magnitude and the angle, so I'm going to have to do the x component, which is going to be magnitude of c cosine theta c, right? Okay, so then that's going to be 4 times cosine of negative 30. Okay, and I end up getting 3.5. And then for c sub y, I would do c uh, sine theta sub c, and that would give me 4 times the sine of negative 30, and that gives me c sub y is equal to about negative 2. Okay? And when I say negative 30, by the way, here's what I mean. When we say that this is directed at negative 30, here's like my coordinate grid, okay? Vector c is then directed maybe something like right here, okay? And then this angle right here is negative 30, okay? Hopefully that makes sense, okay? Okay. Oh, it wants me to plot the two vectors on the grid. Okay, well, A, we already said had a component, what was it? It had negative 3, negative 4, right? Okay, so then 1, I'm going to use a different color. 1, 2, 3, 1, 2, 3, 4. Okay. I don't have my ruler with me, so this is not going to look very pretty. Okay. And then C, what had a magnitude? Well, we've got the components already. It was 3.5 comma negative 2. Okay, so then 1, 2, 3 and a half, 1, 2. So it should be right about there. Okay. Okay. So there you go. Okay, I just drew them both on that polar coordinate. Okay, adding, subtracting, multiplying by scalars. This is something that we did last year. Okay, you can add and subtract vectors, but only with components. Okay, you can't just add them directly unless they're going in the exact same direction. Okay, rectangular form. Okay, to add the vectors, you just add the like components. So add x's to x's and y's to y's. And then to subtract the vectors, you just simply subtract like components. Okay? To multiply a vector by a scalar, you just multiply each component by the scalar. Okay? Really easy to multiply vectors. Okay? Okay, let's look at a couple of examples here, right? So, really quickly, okay, I'm going to write ordered pairs for each of these vectors, okay? Um, so I can see that A has a x component 1, 2, 3, 4. So 4 comma 1, 2, 3. Okay, so it looks like we really like to use 4 comma 3 over this Pythagorean triple. B is negative 2 comma 1, and then C is 0 comma 1, 2, 3, 4, negative 4. Okay. Okay. So, those are the components. Okay, so then if I take a plus b, right? If I'm doing a plus b, okay, then I'm going to take, a vector and b vector, okay. And here's what I'm going to do. I'm just going to take, 4 comma 3, negative 2 comma 1, and I'm just going to add the like components. 4 minus 2, that's going to give me 2. Okay, and then 3 plus 1 is going to give me 4. Okay, so the resultant, which I'm going to call R, is going to have 2 comma 4. So let me draw my vectors, okay, head to tail. Okay, so 4 comma 3, so 1, 2, 3, 4, 1, 2, 3. There's A, okay. B is negative 2. So I'm going to start at the end of A and then draw B from there. So negative 2, comma 1. So my resultant should go over 2 and up 4, right? So let's verify and make sure that works out. Okay, over 2, 1, 2, 3, 4. But perfect. All right, good. I did it right. All right. Not that there was any doubt. A minus B. Okay, well here's what I'm gonna do. If you're gonna subtract it, you can do the head. You can do head-to-head method where you connect the vectors head-to-head. I think the easiest way to do it is just make B negative and make this expression A plus negative B. I mean, that's the same thing, right? That's what I think is going to be the easiest way to do it. So I'm going to do A and negative B and add those together. Okay, so A we already said was 4 comma 3. And B, I'm just going to make both the components negative. 2 comma negative 1. Okay? And so now I can do it pretty easily. This is going to be 6, and then 3 plus negative 1 is going to be 2. So there's my resultant components. Okay? So now I'm gonna draw them on the grid. Okay, A is 4, 1, 2, 3, 4, 1, 2, 3. Okay. B is 2 comma negative 1, so that would be, oh gosh, I don't really have like room to draw it here. Okay. It would be, let's see, 2 comma negative 1, which would be 1, 2, it's like something like right here-ish. Okay. I guess it would be, yeah, kind of right there. Okay. There's negative B. Okay. And then your resultant, it should go over 6. So 1, 2, 3, 4, 5, 6, and up 2. 1, 2. Yeah, that's right about right there, right? Okay. If you do the head to tail method, then you'd start them both at the origin and draw them as normal, and then connect from B going to A, and it gives you the same thing. It gives you the same length of vector. Okay, to do all three of them, you're just going to do A equals 4 comma 3, B equals negative 2 comma 1, C equals 0 comma negative 4. Okay. And add them all together, and your resultant vector, let's see, is going to have, okay, 4 plus negative 2 is just 2, and then 3 plus 1 is 4 plus 4, sorry, minus 4 is 0. So we should end up with this right here, 2 comma 0. And so now I'm going to draw all of the vectors on here. Okay, 1, 2, 3, 4, 1, 2, 3. Okay, there's A. B is negative 2, 1, 2, comma 1. Okay, there's B, and then C is 1, 2, 3, 4. Okay, and then your resultant would just connect straight from the origin right across to there. Okay. Not done yet. I mean, there's more. Okay, don't celebrate yet. Okay, because there's plenty more vector stuff where that came from. 2B, or not 2B. Okay, well, if B is simply negative 2 comma 1, okay, then 2B is just going to be those components multiplied by 2, negative 4 comma 2, okay. So we go 1, 2, 3, 4, 1, 2, okay, and there you go. That's 2B, okay. Negative A, well, if A was 4 comma 3, this is just multiplying them both by negative 1, okay, so you would get negative 4 comma negative 3, and then 1, 2, 3, 4, 1, 2, 3, okay, there's negative A, okay. And then A plus 2B plus C, so that's just going to be very similar to what we just did. A is 4 comma 3, B is negative 2 comma 1, or sorry, 2B would be, gosh, okay, negative 4 comma 2, okay? That's 2b. And then C, we already got was, shoot, what was it? 0 comma negative 4, I'm pretty sure is what it was. Yeah, 0 comma negative 4. 0 comma negative 4. Okay? And when you add them all together, you get a resultant with components. Let's see, that's going to be 0, okay, comma, 5, 1. Okay? And so when I draw all of them together, A is going to be, 1, 2, 3, sorry, yeah, 4, 1, 2, 3. Okay, there's A. B, 2B is going to be negative 4, so 1, 2, 3, 4, 1, 2. Okay, that's 2B. Okay, and then 1, 2, 3, 4. That's going to be C. So your resultant literally just comes from the origin and goes straight up 1. Okay? Okay. A couple properties about vector operations. Vector addition is commutative and associative with that, and what that means. So commutative means that if you do A plus B, it's the same thing as doing B plus A. In some cases, that's not true. Okay? It's weird. Okay? It's associative, which means that if you do A plus B inside of parentheses and then add a C on the other end, add C outside the parentheses, it's the same thing as if you do A separately and then add B plus C in parentheses as well. You're probably thinking, wait, this is pretty obvious, right? It's the same thing, except it's not quite. Vector operations are kind of weird, okay? Vector subtraction is what we call anti-commutative, because what that means is that if you subtract if you do A minus B, it's not the same as B minus A. So you actually have to throw on a negative to make that true. So if you want to swap the directions, you have to throw on a negative to make it true. Okay, if vector A is multiplied by scalar k, then the magnitude is also multiplied by the absolute value of the scalar k. That is absolutely true. Okay, so if you have, for example, we saw this earlier, k times A, right, equals the absolute value of k times the absolute value of A. Okay, that's the same thing. Okay, and then finally, if vector A is multiplied by a scalar, then the direction is either unchanged or has 180 added or subtracted to it, and that's also true. Okay, because if you look right, the angle that k times A make, okay, is either going to be theta sub A if k is positive, or it's going to be theta sub A plus or minus 180 if k is not positive or less than 0. Okay? Let's talk about unit vector, dot, and cross product. Okay? So, if unit vector is a new term for you, you probably haven't heard of it before. We call it the unit vector like A hat or B hat, C hat, G hat, I hat, J hat, whatever, okay? The unit vector is a vector that has the same direction, but it has the same magnitude as something else. So if you have a vector A, the unit vector associated with that vector A is the same thing, but it only has a magnitude of 1. Okay? And if you notice it, then if it's literally just if it's the same direction, right, it has the same angle, but the magnitude is 1. Okay? And the way to get a unit vector form is you would do A hat is equal to the magnitude of A, or sorry, A over the magnitude of A. Okay. And how that would look is you take the components of each part and divide it by the magnitude. Okay. And that gives you the unit vector. Okay. Okay. We sometimes, so another operation that you need to know is dot product. Dot product is sometimes also called the inner product. So if you see the two, it's the same thing. Okay, and it's a way of multiplying two vectors. The result of a dot product is a scalar, and what conceptually is a dot product? It's basically the degree to which, okay, two vectors have the same direction. Okay? The degree to which two vectors have the same direction. Okay? Okay. So if we're given these vectors, and for example, they have x, y, and z components, okay? Then there's four different ways to calculate the dot product, even though they're all equivalent to each other. The first way, in my opinion, is probably the easiest. You take the x components and multiply them by each other, add to that the y components multiplied by each other, and I bet you can guess what you're going to do with the z components. You're going to add them together too. Okay? That's one way to do it. The other way to do it, the more popular way to do another more popular way to do it is you take the magnitude of the individual vectors and then you multiply it by cosine theta, with theta being the angle between the two vectors. Okay? The last two ways of doing it, in my opinion, are the more confusing ways, and I would avoid using them if I were you, but they are essentially the same as the AB cosine theta. The first one is A, magnitude of A, times the component of B that is parallel to A. Okay? Component of B that is parallel to A. And that should make sense, right? Because it's the degree to which two vectors have the same direction. Okay? The last part is the component of A that's parallel to B, okay, times the magnitude of B. So really, it doesn't matter. You're basically taking the component that's parallel to that vector, because again, same direction, right? Okay. Okay. Cross product is very similar to dot product because it is another way to multiply two vectors. However, the result gives you a vector. So that is the difference between cross product and dot product. Is dot product gives you a scalar, cross product gives you a vector. We sometimes call this the vector product. Okay? It's a way of multiplying two vectors. Okay? The result of a cross product is a vector. Okay? And the definition for this, like another way to define this is the degree to which two vectors, okay, have different directions. Okay? Some equations that we can use to calculate it is, instead of using cosine, we would use sine. So it would be A, B, okay, sine theta. With it, and the direction, this doesn't tell you the direction, but the direction would actually be given to you by the right-hand rule. So back in magnetism, we used the right-hand rule multiple times, and the right-hand rule, the one that we used that was like this, okay, is actually a cross product right-hand rule. Because I want you to notice, right, that when we have this right here, if we're doing the cross product of A and B, okay, so I'm gonna get my right hand right. My index finger goes in the direction of A, okay, that way. B is going to go where my middle finger is pointing, so into the page, and you should see that C is going to be, the cross product of the vectors is going to be directed where my thumb is, and you see that that matches up, right? So right-hand rule is basically just a way to get to find the direction of cross product, okay, in there. Okay, this next part right here is the less common, the less exciting definitions of them. It's simply that this is A, B perpendicular to A. Okay, the component of B perpendicular to A, and then A component perpendicular to B. Okay, and then B magnitude of B. Okay, I don't like those definitions as much. I would really stick with the sine definition. Okay, geometrically, the value is given as the area of the parallelogram. Okay, spanned by the vectors A and B. Okay? Okay, let's do a couple of examples, right? Some more examples. Okay, how do we find the, let's see, how do we find the magnitude? This is really just saying magnitude. Okay, this is really just saying magnitude. Even though there's two lines there, it's really just saying magnitude. Okay? Magnitude of A. Okay? Magnitude of A is just root 4 squared plus 3 squared, okay? And that's going to give us 5 because it's a Pythagorean triple, okay? Root 3 squared plus 4 squared plus 12 squared. That's going to give us 13. Okay, we did that earlier. Okay. A dot B, right? To do that, we're just going to do AX BX plus AY BY plus AZ BZ. Okay. So I take the x component of A, which is 4. Okay. X component of B, which is 3. Add the x component or the y component of A, which is 3, y component of B, which is 4, and then the z component of A, which it doesn't have, so it's 0, and then the z component of B, which is 12. So you would notice this part right here cancels out because it's 0, and you end up getting, oh, 4 times 3 plus 3 times 4, that's 24 because it's 12 plus 12, right? Okay, the unit vector for A, okay, all you're going to do is you're going to take the x component over the magnitude, y component over the magnitude. Okay, x component is 4 over the magnitude, which is 5, I hat, plus 3 over 5, j hat. Simple as that. B hat, okay, is going to be the 3 over 13, I hat, plus 4 over 13, j hat, plus, or sorry, minus 12 over 13, k hat. Okay? And then the angle between the two, to figure out the angle between the two, if I do the dot product A dot B equals the magnitude of A, magnitude of B, cosine theta, I can work backwards and get what theta is going to be. So I know A dot B, where I solved earlier, was 24. I know that the magnitude of A is 5. I know the magnitude of B is 13. And I don't know what theta is, so it's cosine there. So when you solve it out, right, 5 times 13 is going to give you 65. Okay? 65. So then what you would do, okay, is you divide that on the other side. You would get cosine theta equals 64. Oh, sorry, not 64. It would be 24 over 65. And then you should see that it would be, you have to use the inverse cosine. Cosine -1 of 24 over 65 would then give you your answer. And then you'd calculate that out to get theta equals 68 degrees. Okay? You got to make sure you're in degrees for that one. Okay. Derivatives of vector functions, really easy. All you got to do to take the derivative of a vector function is just take a derivative of each component. Take derivative of each component. Okay? So you treat I, j, and k as constants, which means you're just going to leave them alone. Leave them alone, okay? So, for example, if you have, here's your vector r. We want to find the first and second derivatives of that. Okay, so let's find the first derivative of r, okay? What I'm going to do is I'm just going to take the derivative of everything that comes before I, j, and k, so I'm just leaving I, j, and k alone. What's the derivative of this? Well, let's see. With respect to t, okay, it's with respect to t, you can see, okay, 3t minus 1, okay, well, the 1's going to get canceled out, so we're just going to be left with 3 I hat plus, okay, that's going to become 4t minus 4. So then 4t minus 4 j hat. And then you'll notice that k hat, 6 doesn't have any x attached to it, so it's going to be 0. So there's no component in the z direction. To take the second derivative, you're just doing the same thing again. Well, now 3i gets canceled out, and you're just going to be left with 4 j hat. Okay? A particle has a position which can be given as a function of time, which is this. Okay? If we were to describe the path that this is taking. So in the x direction, it goes out 3. So in the x direction, the x component of the so this is a position given in vector notation. The path of the particle should be a circle of radius 3 centered on origin. Okay. To find the velocity, this is saying the derivative. Okay. And you're going to have to notice that I'm going to have to kind of chain rule a little bit here. Okay. I'll have to chain rule here. So to find the velocity, okay, what I'm going to have to do is my exterior function is going to be this 3 cosine. My interior is going to be 2t. Okay. If you take the derivative of that, right, it would be negative 3 sine 2t times the derivative of the interior, which is just 2. And so I would end up getting negative 6 sine 2t, okay, I hat. And it's going to look very similar for the other one. It'll be, but this time instead you don't have to worry about the cosine switching signs. It'll be 6 cosine 2t j hat. Okay. When you take the derivative again, okay, to get the acceleration, okay, you should end up getting, and of course, you could try that on your own, but you should end up getting negative 12 cosine 2t, okay, I hat, plus, or not negative, sorry, 12 sine 2 t j hat, okay. Okay, and let's see. Oh, sorry, it should be negative right here. It shouldn't be positive. It should be negative right here. So there we go. Okay. Please tell me that's it for vectors. Yeah, that's it. That's it for vectors. All right. Wow, that was a lot of vector stuff. That was really fun. Okay, vectors. Have fun.